So now that we've set up some basic equations, we have a complete scheme for solving flow problems in pipes. We have our extended Bernoulli equation, where we have the mechanical head at the inlet and the mechanical head at the exit, and then the head loss terms. And we have our friction factors for both laminar and turbulent flows. And then we can get our minor loss coefficients and equivalent lengths from tables. Usually we know the basics. We know what the system looks like, the diameter and length and so on, and what it's made of. You know, the fluid, the material of the pipe, and so on. And then we usually have two different types of goals. The first class consists of either finding pressure drop or finding length, given all the other parameters. These are straightforward, and if we know the Reynolds number, we can obtain the friction factor and we can complete everything else and solve the modified Bernoulli's equation or extended Bernoulli's equation. The second type require iterative calculations. In this case, the flow rate or the diameter varies, and so the Reynolds number isn't known until we finish solving the problem. So we solve these kind of problems with a procedure. We start with step 1 by guessing the friction factor. In step 2, we solve the problem with that friction factor to find the velocity or the diameter required. And then in step 3, we check our guess, and we see if the Reynolds number that we have gives us the same friction factor that we guessed. If the guess was correct, we're done, but if it's not, we need to update our guess and repeat. This is a case where it's usually a good idea to use the fully rough zone friction factor as your initial guess, because it should be reasonably close. The math is actually pretty straightforward here, because we're just solving the modified Bernoulli's equation multiple times. So if we set the problem up in MATLAB, Excel, or some other computer tool, we can iterate very quickly just by changing our guess for the friction factor. We also need to look at interconnected networks of pipes. We don't almost never predict a single pipe. If you look at your house or a building or a nuclear reactor, we have this interconnected network. So these are much more complex and time-consuming than single problems. It's similar in terms of analysis to electrical circuits. We have various sections with different lengths, diameters, and roughness. You can have serial or parallel connections. These types of problems almost always require iterative solution, since the friction factor depends on the flow rate, and you don't necessarily know how the flow is going to be distributed through each of the sections. So velocity in each section is an unknown. We have a potential, which is our hydraulic grade line. The flow rate is our current in our circuit analogy. However, the resistance is kind of complicated because the resistance depends on the current, whereas in an electrical circuit, resistance is more or less a constant. So we have to solve our extended Bernoulli equation to do that. Typically, we perform these solutions using Excel or MATLAB or some other tool. We set up the extended Bernoulli equation for each pipe section, and then we solve n equations simultaneously. Now there are a couple of rules. The first is at each junction the mass flow in has to equal to mass flow out, and that's just from conservation of mass. The second one is that each junction, anywhere two pipes join, there's a unique pressure head or hydraulic grade line, so the pressure is the same at each junction, no matter which path you take to get there. So two pipes with the same endpoints must have the same pressure drop, and the flow rate should be balanced between those to ensure that the pressure drop is the same. So if we take a look if we have junction 2 and junction 3, the pressure drop in this line is the same as the pressure drop in this network. So the pressure difference between 2 and 3 has to be the same no matter which path you take. And the total flow rate from 1 to 2 has to be the same as the total flow rate from 3 to 4, and the flow rate through this section plus the flow rate through this section has to equal that total flow rate.